Hi Math 2. This is Unit 7, Lesson 5, Additional Notes. So you should have a handout with you that looks like what you're seeing on my screen right now. It is two-sided. This first side, questions 1 through 7 that you're looking at, we're going to be doing during this slideshow. And the back side we'll be doing when we do Unit 7, Lesson 6 and 7, the next two lessons. So if you haven't printed this yet, pause the video and go to your Google Classroom and print out the handout. Or if you're unable to do that, go ahead and write and draw these diagrams on your own sheet of paper and then come back to this video. Thank you. So this is a modified lesson 5, more adaptable to being outside the classroom. We have two goals today. One, we're going to construct a circumscribed circle about a triangle. So as a reminder, circumscribed means to be on the outside. So our triangle will be on the inside of our circle. It'll be inscribed. We're also going to prove using words of representation that the perpendicular bisectors of a triangle's sides are concurrent. Concurrent means to intersect. So, and that intersection point that we're going to find is also going to be the center of this circle that circumscribes the triangle. So they're going to be interrelated to each other. So let's start off by looking at this diagram. So in this diagram, there's a lot of things going on. I'd like to draw your attention first to the dotted lines. So there's a dotted line I'm highlighting in yellow, and there's a second dotted line I'm highlighting in yellow, and here's my third dotted line that I'm highlighting in yellow. So this dotted line that you're looking at, I want you to focus on those for the moment. Each one of those are the perpendicular bisector of that side of the triangle. So let's look at the side CB. Let's focus in on this side. This would be its perpendicular bisector, meaning that it goes through the center, the midpoint, it bisects it. It's perpendicular to side CB, and it splits it in half. And if you can faintly see the arcs, if you remember back at the beginning of the school year, to construct a perpendicular bisector, we'd put our compass on C and we draw this big arc that you see over here. We put our compass on B and we get this big arc that you can see over here. And then we would look at where my two arcs intersected, and we'd use that to help me draw in the perpendicular bisector of that segment. So I'd like to erase those dotted lines because there's a lot going on in my picture already. And so I'm going to erase those lines I just drew. So if we went through to all three sides of our triangle and constructed the perpendicular bisector, we'd get the three dotted lines that you see that I highlighted in yellow. So now we see those. They all intersect at the same point. This is point P. That's what we meant on the previous screen about being concurrent. They all intersect at the same point, and that point would be point P. So point P is where my perpendicular bisectors intersect, and we call that a circumcenter. So point P is a circumcenter. That means where the circumcenter is where my perpendicular bisectors intersect. So let's take a look at the next page. On this page, it talks about how the three perpendicular bisectors are concurrent. They meet at a single point called our circumcenter. We just discussed that on the last slide, that P is my circumcenter. So what's special about P? So I'd like you to take a moment and look at the green, pink, and blue lines. If you look at the green, pink, and blue lines, notice that that connects our point P to C, B, and A. Those are the vertices of my triangle. What seems to be true? What do you notice about these three links? Do they appear congruent to you? So a cool thing about my circumcenter is that it is equal distance to the vertices. So the circumcenter is equidistant to the vertices. So it's the same distance from P to C as it is from P to A as it is from P to B. So on this particular one, it talks about circumscribing a circle around our triangle. So in this particular case, our red circles are circumscribed about our triangle. Notice that in this diagram, my red circle goes through all 3 of my vertices. So the purple lines that you see right here, the purple lines are my perpendicular bisectors. So let's go all the way back to the beginning for a moment. The dashed purple lines, those are my perpendicular bisectors of each side. So for example, this perpendicular bisector goes through the midpoint of a side of my triangle and is perpendicular to it. All 3 of these perpendicular bisectors are meeting at one point. That point is the point that we call the circumcenter. That's the point that is equal distance to all 3 of my vertices. And so I can use that as a radius. That would be the radius of my red circle. I can use that distance from P to any one of my 3 vertices, because they're all the same. I can use that as my radius and draw a circle that goes through all 3 of my vertices. And over here, again, my perpendicular bisectors all intersect at a point. That point is my circumcenter, and it is equal distance to this vertice as it is to this vertice as it is to this vertice. And so that's a great radius of my circle that's going to go through all 3 of my vertices. So let's take a look at the 3 different types of triangles and the 3 types of circles that we can circumscribe. So in this graphic, we have an obtuse triangle. So this triangle that you see in this graphic is obtuse, meaning that it's got an angle that's greater than 90 degrees. So there is an angle greater than 90 degrees. Right here, this angle is an obtuse angle, making it an obtuse triangle. In this particular sketch in the middle, this is an acute triangle. You might have said, oh, that looks like an equilateral triangle. I think it does too. But an equilateral triangle is an acute triangle in that all the angles are less than 90 degrees. So the third and final one is a right triangle. So this is a right triangle, meaning that it has an angle that is 90 degrees. So I've got an obtuse triangle, it's got an angle greater than 90. I've got an acute triangle, that's all 3 angles are less than 90. And I've got a right triangle, that means one angle is 90. So let's notice in these where my circumcenter is. So in this case, my circumcenter, let's call it P. My intersection point of my 3 perpendicular bisectors is point P. In this diagram, it's again point P. And in this diagram, my 3 dotted lines intersect again at my point P. So let's take a look at the location of point P, because this is significant. What do you happen to notice about the location of a circumcenter of a obtuse triangle in the first diagram? Are you noticing that it looks like it's outside the circle? It's outside, not the circle, I'm sorry, the outside the triangle. And then when you look at the circumcenter of an acute triangle, are you noticing that the circumcenter is inside the triangle? And then finally, when you look at the right triangle, where does the circumcenter seem to be? on the triangle. The circumcenter seems to be on the triangle, and it's not on the triangle just anywhere. That right there happens to be the midpoint. I'm going to abbreviate that if that's okay. The midpoint of the hypotenuse. Well, that's pretty useful. Midpoint of the hypotenuse. Let's take a look at our next slide, shall we? So this diagram is what we just talked about on the last page. So let's take a look at these three triangles. What do we notice here? This first triangle, let's look and see where that red circumcenter is at. And then finally, we'll call this triangle 1 in that picture. This will be my triangle 2. Notice where that circumcenter is at. And this will be my third triangle. This is my right triangle. Let's also notice where that red circumcenter is. So again, the blue lines you're looking at are the perpendicular bisector of the side. There's 3 sides to a triangle. There's 3 blue lines. You can see the right angle mark right here that goes with this blue line. It's the perpendicular bisector of this side of the triangle. There's 2 other sides of the triangle. There's 2 other blue lines, and they intersect at my red circumcenter. That's true about all 3 of these diagrams. And for the triangle that was an acute triangle, notice my red circumcenter is inside the triangle. For my obtuse triangle with my really large obtuse angle, notice that it was outside the triangle. Oh, sorry about that, outside the triangle. And finally, on my third diagram, notice that circumcenter where my 3 blue lines are meeting, my 3 perpendicular bisectors. This is on my triangle, and it's not on my right triangle just anywhere. It's on the midpoint of the hypotenuse of my right triangle. So this red dot is the center of a circle that would circumscribe my triangle. In order to do the circle, do you see this yellow line in the first diagram? Are you guys looking at this yellow line? This is the distance from my red dot to this vertice, and that happens to be the same as the distance from my red dot, my circumcenter, to this vertice, and it happens to match the distance from the circumcenter to this third vertice. That's because my circumcenter is equidistant to all 3 vertices. So that yellow distance is the radius of my circle. If we were at school, you'd put your pointer on the red dot, you'd put your pencil on any of the 3 vertices, and you'd softly draw in the rest of your circle, and you would circumscribe a circle about your triangle. Let's take a look at the next screen, shall we? So this is where I would like you to get that extra page in notes I was talking about. We're going to start using that extra page of notes. So let's take a look at the first problems. So let's begin at the top of our worksheet. So K, L, and M are each something. So let's take a look at this. This diagram, we have to understand all the different parts. So let's start at the beginning where it says that KZ, LZ, and MZ are the perpendicular bisectors. So let's pause and look at KZ, which is this length, and LZ, which is this length, and my MZ, which is this length. Those are the perpendicular bisectors of the triangle. So notice the right angle. Notice the right angle, and notice the right angle. And notice that they all intersect at Z. So for starters, when it asks me what is K, L, and M, those are each the midpoints of their respective sides. If that is a perpendicular bisector, it means that it's perpendicular to the side and it bisects it. In other words, it splits it in half. So K, L, and M are midpoints. We're going to use that in our problems. What's Z called? Well, Z is where the perpendicular bisectors intersect. This is where the perpendicular bisectors, I'm going to abbreviate it, intersect. and we learned that that is called the circumcenter. And point Z is equal distance to the what? So our circumcenter is equal distance, and let me change the color that I'm writing with, is equal distance to my 3, I'm going to use 4 since I haven't used 4 anywhere else, to my 3 vertices of my triangle. So if we were in the classroom, you could grab a compass and put your pointer on Z and your pencil on H, and as long as you kept your radius set to ZH, as you spin it around, you'd go through all the vertices, creating a circle that was circumscribed about your triangle. That's what you can do with a circumcenter. So let's take a look at the next problems on the page. So it says here that in this diagram, KZ, LZ, and MZ are the perpendicular bisectors. We just looked at that up above. It says use the given information to find the length of each segment. Note that the figure is not drawn to scale. I know you can see the answers there, but we need to know how to do the math behind it. So let's check this out. So if ZM is 7, so notice that's been drawn on our diagram already, and ZJ is 25, so notice where that is, and HK is 20. It wants me to find ZH, so let me go find ZH. So I'm looking to find this segment. Okay, I need to find that segment, and I also need to find HG. HG would be this entire side. So let me start using some information that we know. We happen to know that my perpendicular bisectors intersect at the circumcenter. So right here, Z is my circumcenter. So I know that it's equal distance to the 3 vertices. So I happen to know that ZH is equal to ZJ, which would be equal to ZG. So from Z to all 3 of my vertices is the same distance. So if ZJ is 25, then all 3 of those distances are also 25 units. So I know that ZH is 25 for that reason. So now let's talk about HG. If ZK is a perpendicular bisector, so this is a perpendicular bisector, then it bisects HG. It divides it in half. It splits it. It's splitting it in half. K is a midpoint. So if KH is 20, then I know that KG is also 20. So the entire distance then would be, you're correct, 40. Nice. So now let's take a look at this next problem. Again, the information's highlighted for me. I know that HG is 36, so this entire, 136. The entire distance is 136. I know that HC is 70 or is 85, and I know that MZ is 13. So it asks me to find, there it goes. It asked me to find KG. It asked me to find ZJ, so first of all, KG, I'm going to find this distance right there. It asks me to find ZJ, so let's go identify ZJ as this distance right here. Okay, and I also have to find KZ, so let's go find KZ. KZ is right here. Okay, ladies and gentlemen, so let's get started. KG. Well, if the entire distance is 136, then it follows, if this is a perpendicular bisector, and that makes K my midpoint, that both KG and KH would add up to 136. So each side would have to be half of that. So if you divide your 136 by 2, you get 68. So my KG then would be 68. Moving on to ZJ. ZJ, Z is my circumcenter and J is one of my vertices. And I know that the circumcenter is equal distance to all 3 vertices. So if from Z to H is 85, then Z to J is 85, and Z to G also would be 85. So I happen to know that that's 85. The circumcenter is equal distance to all 3 vertices. So now KZ is our last one to figure out. I happen to know that from the first part of this that KG is equal to 68, and so is KH. They're both 68. And I happen to know, because I was told in the problem, that HZ is 85. I could use this red right triangle and the Pythagorean theorem to find my missing side, KZ. So my hypotenuse is HZ, 85. And so I could set up my Pythagorean theorem. I know that 68 squared plus KZ squared equals my HC, which is 85 squared. And you've got a little bit of math to do, so you could grab out your calculators and go ahead and square the 68, and you would get 4,624 plus KZ squared equals 85 squared. We should have 7,225. And when we subtract over our 4,624, we get 2,601. Now we're going to take the square root of both sides, and we're going to find that we get 51 for KZ. So KZ would be 51 in length. Looking at our next slide, so this is where students in class would now go do 6 and 7 together. So let's take a look at 6 and 7. These problems are identical to the last problems we were just doing. So if I could write in the answers, just like in the class, give these a try and see if you get the correct answers. And if you don't, come to Zoom or email for some extra help. But when you calculate it, your ZJ should be 65 and your HJ should be 126. And finally, in the last one, when you calculate it, GM should be 60, ZG should be 65, and JZ should also be 65. So that concludes the additional notes for Unit 7, Lesson 5. Thank you.